recording ever.
Okay. So, welcome everyone to the second installment of Virtual Geometry Structure Seminar. So, our today's speaker is Professor Stephan Tillmann from Sydney University, and he's going to talk about the title of his talk is "What is the Thurston norm?" So, Professor Tillmann, over to you.
Yeah, thank you very much for the invitation to speak here. So I'm speaking here from the University of Sydney, which is on the traditional land of the Gadigal people of the Eora Nation. And my title, yes, I wanted to explain what the Thurston norm is. So I think Krishnendra said that this might be a nice topic. Let me just share my iPad. Okay. Can you see the screen?
Yes.
Yeah, perfect. Okay, so I haven't prepared sort of slides. I'll do this on the fly, and so please do interrupt and ask questions as you go along. So the title is "What is the Thurston norm?" Okay, so let's maybe start with surfaces. And if I say too many things that are too well known, just yell at me and I'll sort of speed up. So S is an orientable surface. Of genus G greater or equal to 0 with n punctures. And I will always assume actually that my Euler characteristic is negative. Yeah, so assume, well, I guess not my Euler characteristic, the Euler characteristic of the surface. Yeah, so it's 2 minus 2g minus n. Yeah, okay. And so if you take a homeomorphism of the surface, so let phi from S to S be a homeomorphism. Then you can build what is called a mapping cylinder. So you can build a 3-manifold M phi, which you get by just taking the surface times an interval and then identifying the points in surface cross 0 with points in surface cross 1 via the homeomorphism. So this is, so to draw sort of a schematic, here's my surface, if it's genus G with 2 punctures. I think of this as times an interval. And then what phi does is sort of glues the bottom to the top somewhere. Yeah, so this is the action of phi on the surface. Okay, and so this is often called the mapping torus. Yeah, or also one says that M fibers, so M phi fibers, yeah, over the circle with fiber, in this case S. Okay. So I guess here I should say the mapping torus of phi. So this is a very nice construction for a 3-manifold, and I guess it seems very special. But let's just sort of carry on with this for a little bit. So there's a natural map F from this mapping torus to the circle, yeah, such that the preimage of any point on the circle is just a copy of S, yeah, for all x in S1. Okay, and so this is exactly what we sort of mean when we say it's a bundle, yeah. And so up to homeomorphism, this three-dimensional manifold that I've built M phi only depends on the isotopy class of phi in the mapping class group of S. Mapping class group of S. Yeah. So this is orientation preserving homeomorphisms modulo isotopy. Okay. So the question is now, what can we say about the topology of this three manifold, right? We have a nice three manifold here. And this is actually related to the dynamics really of this mapping class. So there's a Nielsen-Thurston classification. And so what is this? Really this, what it tells us is there's really only three different types. Yeah, three different types of mapping classes. And so each phi in the mapping class group of S has a representation or representative that is either periodic, so i.e. has finite order, just to give an example, right? I mean, I could sort of draw a surface maybe like this here. I said I want Euler characteristic to be negative, so let's put in some genus here. Right, and so once you have this, you can sort of imagine just taking sort of a rotation here, yeah, and that's a perfectly fine mapping class, right? We just sort of rotate the surface here by 2 pi on 5, yeah, so 2 pi on 5. That's an example of a mapping class of finite order. Okay, or the second possibility would be it's reducible. So that means, i.e., it preserves a set of curves. Okay. And in this example that I've drawn, actually, I guess you have such a thing, right? I mean, if I draw in these curves here, then they're actually preserved, right? They're preserved by this action here, yeah? But you don't necessarily need to be periodic in order to have a preserved set of curves. And then the third option is your pseudo-Anosov. And because we'll use this a lot, usually we just write it as PA, yeah? And so what does pseudo-Anosov mean? So there's a really nice sort of way of looking at it. So there exists some constant lambda bigger than 0 called the dilatation. Okay, and together with it, a phi invariant singular and transversely measured. Put this here. Foliation. And actually, there's two of them. So written F plus minus, and the measures are mu plus minus, such that, well, phi preserves them. So up to this dilatation. So phi of mu plus minus is equal to And so it just multiplies by lambda plus minus 1, mu plus minus. Yeah, so the foliation sort of indicated with a plus. The measure is just multiplied by plus, yeah, by lambda, and the measure that I indicated with minus is actually multiplied by lambda inverse. Yeah, so this is how the action is on these measures. Okay, and so just to draw sort of maybe a picture, a local picture is, I mean, if you sort of think about this kind of these transverse foliations that you have here, right? So one is basically then sort of expanded, and the other one is kind of contracted. Yeah, so maybe if lambda is the if lambda is bigger than 1, right? So maybe then this here is the lambda inverse action. So you're kind of contracting things, yeah. Whilst in the lambda direction, sort of things become further apart. Yeah. So this is sort of multiplying the measure by lambda. Yeah. And then, I mean, singularities, I mean, they sort of look a bit like this here, where this is a sort of point here, and well, you have this kind of foliation, and then the transverse foliation just looks like this here. Yeah, so locally, I mean, outside of the singularity, everything really looks like this here, but then here's the singularity that has some index. Okay. And so then, so moreover, so what I sort of indicated before, so pseudo-Anosov implies not periodic and not reducible. So this is mutually exclusive, but periodic and reducible are not mutually exclusive. Okay. Are there any questions about this classification? The Nielsen-Thurston classification.
So could you explain again what pseudo-Anosov means?
Yeah. So it's the pseudo-Anosov. So when you look at the surface, so one quick way of saying it is you're pseudo-Anosov if you're not periodic and not reducible. Yeah. So you don't have, yeah, you're not of finite order, you have infinite order, and there's no invariant set of curves on your surface. But that's, of course, maybe not a very intrinsic way of saying what pseudo-Anosov means. So a nice way of looking at pseudo-Anosov is you can find on your surface, you can find these kind of foliations. So let me maybe try to draw it on the surface. So here's maybe your surface. And then on the surface, you find these foliations. So I mean, that's always a bit hard to draw, but anyway, I'll try to draw something, right? And whatever these foliations do, I mean, they're sort of and I should also draw sort of the other one. So here's maybe, let me draw this in blue. So the this one here. All right, so this is kind of what it looks like. And so you have these kind of two foliations. And so then if you apply phi, what happens is that basically the, say the red one gets sort of stretched out in this case, and the blue one gets contracted. Yeah, so this is what this looks like. I have my life very easy here with this example, but yeah, so maybe these blue curves that you've seen here, that become sort of very close to each other. And then these red curves that I've sort of drawn, they all of a sudden become sort of further away from each other. Yeah. So that's and the singularities are sort of fixed. Yeah. So that's kind of what pseudo-Anosov pseudo-Anosov does for you. Yeah. Okay. And so here's another way of maybe understanding these this classification a little bit better. I mean, I said we construct this manifold M sub phi, right? And so here's a theorem by Thurston. So we're assuming still that the Euler characteristic of the surface is negative. And so then he says there's the following three cases. So if phi is periodic, then this manifold M sub phi is modeled. So it has a curvature. Sorry, it has a geometry, homogeneous geometry, and it's modeled on H2 times R. So a hyperbolic geometry, two-dimensional hyperbolic geometry times Euclidean geometry. And the second case, so if phi is reducible, then M phi contains a pi1 injective torus. And the third thing is if phi is pseudo-Anosov, then it actually has a hyperbolic geometry. It's hyperbolic. So a constant sectional curvature geometry. So let me maybe remark on these properties. So for the first one, I guess the forward direction really just comes from the fact that, I mean, if you think about H2 times R, yeah, H2 times R is the universal covering of your surface as Gn times R. Yeah, because you here assumed I have negative Euler characteristic. Yeah, and so universal cover is naturally the hyperbolic plane. Yeah, this is my uniformization, and then I have a finite cover just from the fact that phi is periodic or finite order. So there's a finite cover to M sub phi. Okay. So this is how one can sort of see that I can really put this geometry, right? I mean, on this surface here, I can put hyperbolic geometry. So I get, yeah, this map here. And then I have this finite sheeted covering map. Okay. Then the next thing is that, yeah.
So why this cover is finite? Like, I'm not sorry, but I'm not able to see this M phi from SG.
Yeah, this is because phi, phi is periodic, and so I know that phi to the n is the identity, yeah, for some n, yeah, and so then actually I can sort of build. I mean, the nice thing is here I can sort of build covering spaces. So if I think of M, so here's M sub phi. Sorry, let me just draw it like this here. So M sub phi, let me just sort of draw it schematically like this here, right? This here is S, yeah? So I really think of this as, this is my kind of schematic for saying I had taken, here sort of had S times the interval, yeah? And then I think of phi as going top to bottom, yeah?
Yeah.
And so I draw it sort of schematically like this here, the glowing effect, right? And so now basically you can sort of see if I now cut along the surface, really, and I make myself 2 copies of this that are glued together. So you see something like this here, right? So then what is the, so here the monodromy map going around is phi, right? So this tells me how I've really sort of identified things, yeah? This is the monodromy here. If I think about sort of these intervals here, right? I mean, under phi, they sort of I get this kind of flow, yeah? I come along here, this point's identified somewhere here. I keep going, it's identified somewhere here, and so forth, yeah? So this is how I can sort of view phi also as a monodromy here. And so you see here, this is really phi squared, yeah? This is the same as taking sort of basically 2 stacks of this here, yeah? And gluing by phi squared, yeah? This is what you get here. So this here is m phi squared. Okay, and so this of course works for any n, right? So here, if I sort of take this here, and I do this now as an n-fold covering, yeah. So here I have yeah, and I guess here I should have said this here is really a 2-to-1 cover, yeah. And here I can sort of build an n-to-1 covering if I build m phi to the n, right? But now if phi to the n is the identity, then really I've just glued top to bottom as they are, and I just get, oh, sorry. So now I know what you're referring to. Why is this a final cover? Yes, it's not, because I haven't written the circle here, but yeah, thank you. Okay, so yeah.
Sorry, I should guess that, but yeah, sorry, I just confused.
Yeah. Sorry, that there was yeah. So this here is right. So now everything's happy, right? So this is m for the identity, and this is really s times, yeah, s times s1. Okay, yeah. Very good. Yeah, thanks for that. So yeah, here I shouldn't have written here I should have written s1 here. So this here is a yeah. Thank you. Oh, thanks a lot. So then what did I want to say about the second case? So the second case is basically the so this is the forward direction here, and then the backwards direction is not too hard. So so one backwards, not too hard. But I don't want to spend any time on this. And then the let's talk about the second one. So the second one is this one here. And so, I mean, the forwards direction is basically, so if you have a fixed set of curves, so let's say, yeah, alpha I is a fixed set of curves, then what you do is just you take these curves times the interval on your surface, and you identify using phi, and this gives you what turns out to be an essential torus in m phi. Yeah. Okay. And again, then the backwards direction is again not too hard. And then the third case, and that's really the difficult bit. Yeah, so that's kind of the hyperbolization theorem for circle bundles, yeah, with pseudo-Anosov. Okay. Yeah. And so you could contrast this now with the just with the torus, right? I always said negative Euler characteristics. So contrast this with the torus. S1 times S1. So the mapping class group of the torus, which is SL2Z, And there's basically sort of a classification where you say, well, I mean, if the trace of phi is less than 2, or phi is plus minus the identity, that's if and only if phi is periodic. And that's if and only if the bundle that you get is actually Euclidean. And then there's the case where the trace of phi is equal to 2 in absolute value, and phi is not plus minus the identity. Sorry, I should probably close the window.
So lots of rain.
Sorry?
Lots of rain.
No, it's actually, there's people repairing, they're changing cladding on the buildings down there because it turns out all this cladding is flammable. So I think that's trying to keep us safe. Of course, hopefully in this rain, it's not gonna be too flammable. So, so this if and only if phi is reducible. And that's if and only if M phi has nil geometry, so built on the Heisenberg group, and then trace of phi bigger than 2. That's if and only if phi is, well, for torus it's called anosov, and that's if and only if M sub phi has the Thurston geometry that's called Sol or solve. Yeah, that's modeled on solvable group. Okay, so this is sort of the contrast here, that the classification for the negative Euler accuracy case is really quite similar, really, or analogous, analogous to what you have for the torus. Okay, so then there's sort of Thurston's virtual fibration conjecture. Which he conjectured in 1982, and it was proved by Agol, work of Agol and Wise in 2012, and the sort of ingredients by Gross and Manning from 2017. And so this says that every complete hyperbolic three-manifold is finitely covered by a bundle. Or here, a finite volume. Okay. So yeah. And so then, so this is sort of amazing, right? Because every of these hyperbolic manifolds has a finite sheeted cover, that's a bundle. And then there's an amazing fact. Because really, I mean, the structure of a bundle just seems so special, right? I mean, you just think, well, I have the surface, it's sort of fibers in this way, and what else could it do? Yeah. But the amazing fact is that if a manifold is a bundle and the rank of the first homology is greater or equal to 2, then your manifold fibers actually in infinitely many different inequivalent ways. So this is maybe at first you sort of think, I mean, this structure is so special, right? I mean, how could this happen? Yeah, how could you actually achieve this, and how can you sort of see these kind of different ways? And so maybe I want to spend a little bit of time on this, but before that, I sort of want to sort of so put together some ways, different ways of basically thinking about these vibrations and also how one might detect them. Yeah. So let me maybe.
I skipped
So this fact is about three manifold, or it's general, any n-dimensional?
Sorry.
This fact is about a three manifold, or it's about n-dimensional manifold?
Oh,
This
here I'm
fact.
talking about, yeah. Here I'm talking about three manifolds. Yeah.
So what do we mean by covered by a bundle exactly?
Yeah. So that has a finite sheeted covering space that is a bundle. Yeah. So
so you mean that's the total space of the bundle, or?
Yeah. Yeah. So so I guess to say it more precisely, so for let's call it M, yeah, there exists some N, yeah, and that is a bundle, yeah, N that is a bundle, and a finite sheeted cover of M. Yeah. So this is what you get. Yeah. So N covers M by some kind of finite degree, and N has this kind of structure that surface times interval modulo some phi. Yeah.
Okay.
Yeah, so we always have these finite, finite sheet covering spaces of this form, and what we get here is that this, yeah, I mean this. So this gives you one way then of studying all hyperbolic three manifolds, right? I mean, how do you study all hyperbolic three manifolds? Well, you just need to study all bundles and study the finite quotients. Yeah. So in that sense, then maybe bundles are the right class of manifolds to study, because once you understand the bundles and the finite sheet covers, then you have all hyperbolic three manifolds.
One question. So does it imply that the finite sheeted cover will be a mapping torus of pseudo-anisotropy?
Sorry, I mean this one here.
Yeah.
M.
If it is hyperbolic, then the cover N, would it automatically imply that it will be a pseudo-anisotropy mapping torus?
So all you know by knowing that it's a finite covering is that you know this is a three manifold. Yeah, I mean that's, and you also know actually that it will be hyperbolic. But the special thing here is, I mean, what Thurston, what his virtual vibration conjecture says is that you can actually find some finite sheeted cover that is a bundle. Yeah, so that's really the important part here. Yeah.
So N will be hyperbolic, right? Or it may not be hyperbolic also.
N will, so because M is hyperbolic, N will also be hyperbolic.
Okay, and this is a bundle. So will it come for from pseudo-anisotropy torus always, or it can be something else also?
Sorry, will it be what?
It's a torus, pseudo-anisotropy mapping torus.
It will be, yeah. So that's the that is what we say here, right?
Okay, that's the meaning of bundle. Okay.
Yeah, that is really the amazing fact, right? That Thurston says you give me a hyperbolic three manifold, then he says, oh, there is some finite sheeted cover that is actually a bundle that has this very, very special structure. Yeah.
Oh,
Yeah, because at first you would think bundles are very rare, yeah, and you don't have many. And now all of a sudden it seems like maybe there's actually an abundance of covers, abundance of bundles, yeah. And so that's sort of one thing here, yeah. So this really ties, right? This ties basically hyperbolic three manifolds together with bundles as their finite coercions. And then the other amazing fact is that once you have this kind of structure, so once your manifold N has the structure as a bundle, assuming that the rank is at least 2, then you know that it's actually going to be a bundle in infinitely many different inequivalent ways. And inequivalent you can see by basically seeing that the surfaces, the topology of these surfaces is different. So you don't just even need to vary this here. It's really in topology of the surfaces. And so I want to sort of explain how this sort of comes about and how you can find these ways. Let's see. So
so whenever you refer to a bundle, you mean it's a surface bundle over a circle, right? So it's a mapping over a circle.
Yeah. So this is what
that's what you.
Yeah. This is the bundle. Yeah. Mm-hmm. Okay, so let's see. So what do we have when we have sort of a I mean, let me draw things maybe one dimension down, but always just think about three manifolds. So here we said we have this kind of, imagine you just have a map from a three manifold to the circle, yeah? And actually think of both my three manifold and the circle to be oriented, yeah? So there's some orientation here, there's some orientation here, yeah? Okay. And so maybe the pre-image of this point is this circle. Maybe the pre-image of this point is this circle. Well, it's actually consists of two circles, and the third point maybe somewhere. Maybe the pre-image of this point is the circle here. Yeah. So I have some map to the circle. I mean, this here is certainly not a bundle what I've drawn, but that's fine. Yeah. I mean, I'm just thinking now about maps from three manifolds to the circle. Yeah. And so then, I mean, the first thing is that the pre-image of a point is an oriented surface for a generic point. Right, I mean, there is of course points where this is not the case. Like, I mean, if I here, yeah, in this case here, if I think about this one here, I sort of get, yeah, I get a graph, yeah. So this is not a submanifold. Yeah, but generally I sort of see submanifolds here. Yeah, so that's one thing. And the orientation just comes from really using the orientation of the manifold, yeah, and using the orientation of the circle, and that really gives me a natural sort of transverse orientation here, yeah, on these kind of circles. So this is where this comes from. And then the second thing that I have is, well, of course, on the circle, I have the angle form. Yeah, so I can think about the angle form. So, and I normalize it. So it's 1/2 pi d theta. And so I can pull it back to m. And this is a closed one form with integral periods. And then the third thing that I want to bring in this picture here is, of course, the induced homomorphism on fundamental group. Yeah, so I get an induced homomorphism from pi1 of m to pi1 of the circle, which is of course just z. Yeah, so this here is a homomorphism. Okay, and so these are sort of the three sort of key players. And we have an oriented surface, we have a closed one form, and we have a homomorphism onto the integers. Yeah, and of course here in the yeah, really, if I think about this, I mean, if I think about sort of homotopic classes of maps from M to S1, yeah, then really this is the same as H upper 1 of M with Z coefficients. Yeah, this is just because the circle is a K pi 1. And then this here, of course, by the punctual duality, is the same as H lower 2 M rel boundary M with Z coefficients. And then by the universal covering coefficients theorem, this is the same as thinking about homomorphisms from pi1 of M to Z. Yeah. So this is really how I now bring sort of these three things together, right? I mean, here's my map to the surface, to the circle. Here's my form. Here's my oriented surface, and here is my homomorphism. Yeah, and it's really through these kind of isomorphisms that we often like to move between different things and sort of think about this kind of situation here. So now this gives you sort of three different ways of saying what it means that F is homotopic to a vibration. So now F is homotopic to a vibration if and only if, I mean, up to a homotopy M minus F inverse of X is really the same as S times 0, 1 for some surface. It's if and only if I look at this form, is homotopic to a non-singular, non-trivial form. And I mean the homomorphism. So this is a result by Stallings from 1961. So the kernel of this homomorphism that you have here is finitely generated. Yeah, so this is sort of a really nice criterion for saying that something is vibration. I mean, it might seem really bizarre at first, right? I mean, I give you a homomorphism because really this is just a sort of statement now about homomorphisms, right? I give you a homomorphism from the fundamental group of my 3 manifold to the integers, and then if the kernel of this homomorphism is finitely generated, then I basically know that if I construct from this homomorphism the associated map between the manifold and the circle, then that's homotopic to a vibration. So this is kind of it's kind of amazing, right? Where you just use algebra to give you this very nice topological effect. Yeah. I've talked for a long time. I said I was going to say what the Thurston norm is, and I haven't even mentioned it yet. So let me now say what the Thurston norm is. Okay, so for an element in H1 of M with Z coefficients, and dually, I think of this as H2 of M, well, boundary with Z coefficients, define the following. So the norm of phi is kind of Thurston norm. It's a minimum where you take the negative Euler characteristic of a surface, and you say that the surface is dual to phi. Yeah, so it's so we have phi here, and so we're taking all surfaces. So we're taking the minimum over all surfaces in here that are kind of dual to phi under this correspondence here. So surfaces representing homology classes without spherical components. Yeah, so I don't want to count. I mean, if right, I mean, my dual surface, of course, I can just add to it spheres that bound balls, but they're not interesting. Yeah, so we'll just delete them, right? So if in this case here, I mean, if I have a surface that consists, say, of a genus 2 surface and a torus and a sphere, right? So then I would really just throw away the sphere, yeah, and just note down basically 2 as my answer. Okay, so so here are some facts, and I mean the first fact sort of justifies the name norm. So first thing is that this is a norm. If M is irreducible and atoroidal. And so irreducible means every sphere bounds a ball. Atoroidal means there's no essential torus. And I also need to be an annular, which means there's no essential annulus properly embedded in the manifold, and it's boundary incompressible. Okay, so yeah, so this means that the boundary does not admit any compression disks. Okay, so in this case you have a norm. So in particular, if M is hyperbolic, it's a norm. Okay, the second fact is that it extends, because really we've defined it here, we've really used here Z coefficients, but really, I mean, if you think about norms and doing things in vector spaces, R is just much more convenient. So it extends continuously to a unique norm on H upper 1 M with R coefficients, or if you wish, H2 of M, real boundary of M with R coefficients. And so we write, so a norm is really then just defined uniquely by the unit ball. So this is all X and H upper 1 MR, such that the Thurston norm is less or equal to 1. Yeah, so this is the unit ball. And so it turns out that this here, this norm ball that we have, so the norm is a polyhedral norm. So this is a finite-sided polyhedron. Or polytope, I guess. I mean, it's not just three-dimensional. A finite-sided polytope. Okay. So let's maybe, I mean, there's it's really fun to look at Thurston's original paper. So really look at and it's really just called a norm on homology of a 3 manifold. Yeah, so Yeah, so there he gives the following example, because some examples one can really just do by hand, which is a lot of fun. And so here's one. So if we take the whitehead link, so let me just draw sort of the whitehead link. Okay, and let me just give sort of the two components here names, lambda 1, lambda 2, and they're perfectly fine bases to choose. Yeah. So and really I think of so H2 of the manifold real boundary with R, and we said this is the same as you can actually now think of this as really just thinking about the homology of the of L, yeah, this link that I have. So the link L consisting of lambda 1 union lambda 2, so H1 of L with real coefficients. So that's how I will sort of think about it. Yeah. And so let's look at surfaces bounding these things. I mean, here, for instance, if I think about lambda 1, right, I see basically, I mean, here I see a disk that bounds lambda 1, but then has sort of these two. It also hits lambda 2, but I can sort of just use an annulus, yeah, to connect this here up. So like this here, right? So it's clear what I'm doing here. So what I found is, right, I found a surface here, I found a one-punctured torus, yeah, this here. Let's call the surface here maybe F1. So boundary of F1 is lambda 1, yeah, and the Euler characteristic of F1 is -1, yeah, and so this means that the norm of lambda 1 really is less or equal to 1, yeah, since I found the surface, right, and we're taking in doing this norm, we're looking at the minimum, yeah, so the norm says you take the minimum over negative Euler characteristic. So really then the question is, I mean, could it be 0? And in this case, it can't be 0 because I'm looking at a hyperbolic manifold. Yeah. So since lambda 1 is not the 0 class, yeah, I know that the norm of lambda 1 must be bigger than 0. Yeah. And so this implies that the norm of lambda 1 is actually equal to 1. Okay. And so similarly, I mean, for lambda 2, it's kind of the same argument when you look at this. And so so what you see is when you sort of start drawing this, I mean, here's sort of an axis for lambda 1, axis for lambda 2, and my ball will be symmetric about the origin, yeah, because they're just changing orientation, changing the sign. And so what you see is, whoops, what you see here is that you just get sort of at least this here contained in your unit ball, right? I mean, you know that these are on the boundary, these vertices on the boundary of the unit ball. And then you wonder, I mean, could the ball, for instance, I mean, your unit ball could be something like this here, right? It just needs to be some kind of polytope that passes through these vertices. I mean, it could also be something like this here, yeah? So the question is really what about sort of things here along here, yeah? What is the norm here at this point? So really what we should maybe look at is, we should look at the next lattice point, which is this one here. Yeah, so this is the point lambda 1 plus lambda 2. Yeah, okay. So let's see. So let me just add here. So similarly, so you get the norm of lambda 2, this one. And so now we sort of need to think about lambda 1 plus lambda 2. So what about norm of lambda 1 plus lambda 2? And of course, I mean, it's a norm I claimed, right? So we say, well, let's use the triangle inequality. So it's bounded above by 2. And the question is now what can we say about the surface? So any surface actually any surface representing lambda1 plus lambda2 actually must have an even number of boundary components. So it has since there's sort of a symmetry, there's a symmetry exchanging lambda1, lambda2 in this link complement. So which may be hard to see, but that exists since there is a symmetry of L exchanging lambda1 and lambda2. Yeah. But that implies that it has an even Euler characteristic. And now we know that, I mean, because we have no annulus, because it's hyperbolic, this implies that, the norm of lambda1 plus lambda2 is really equal to 2. So if I think about this norm, so the norm here, the values are 1. Here the value is 2, but this means here's a value 1 as well, right? And so now I found sort of, and these points here are collinear. So here, I know now it's everywhere 1 along here. Yeah. So I found the unit ball. So this is basically what we're done. Yeah. So we're done. We've computed a unit ball for the Thurston norm. And so now it can sort of, there's this fibered phase theory. And this is the last bit of information that I will give you, and then I think my time is up anyway, right? So if phi, so in H upper 1 of M with Z coefficients, corresponds to a fibration, yeah, or bundled structure, yeah, then the whole ray, so the ray through this one passes through the interior of a top dimensional phase of this Thurston unit norm ball. So in this example that we just had for the Whitehead link, where we saw this one here, it actually does turn out that this point here corresponds to a fibration. And so, yeah, this sort of gives you this kind of ray through it. Okay, and here's the top dimensional phase, and these are the vertices. And now something else even happens, and this is where we get the infinitely many form. So this is the amazing fact, and this is what Thurston proves in this initial paper on the Thurston norm. And every integral point in the cone so I should give this phase a name. Let me give this phase a name and just call it f sub phi. In the cone, so bigger than 0 times f sub phi, yeah, corresponds to a fibration. Okay, so in this case here would then be, here we have to exclude basically the extremities, but then everything inside here corresponds to a fibration. So let me just sort of shade this. Yeah, and so in particular, I mean, if you look at these kind of integral points that you see here, I mean, so here's one, right? So this point here corresponds to a fibration, And now it's not too hard to see that actually the Euler characteristic function is it's linear on here. Yeah, linear on here, because this is how the norm is defined, right? Here, everything is norm 1. Yeah. And so this means that this surface, the surface corresponding to this one, and the surface corresponding to this vibration, they have different Euler characteristics. So, and that will sort of be true along sort of this cone. Yeah. So this is how you see that you have infinitely many inequivalent vibrations for the same manifold. And they have this really nice structure that are really given by some top dimensional phases of the Thurston unit norm ball. And so this is what you give. So this here is then called the fibered phase. Yeah, this boundary phase here of the Thurston norm. So Fi is called a fibered phase. Okay. And so maybe then I just want to conclude by showing you that there is, I mean, Will Worden in work with sort of Daryl Cooper and Will Worden, we've sort of implemented a nice algorithm to actually compute the Thurston norm. So you can actually do sort of really nice examples on the computer, and everyone can do it. So if I just go here to share this here. So here you see the Will Worden has sort of a nice web page where he lets you from his Git project here download his program called T-norm, and you can sort of play around with it. There's also a sort of description on how to install it and everything. And with this, you get sort of nice pictures like the one that we have in our paper. And maybe I should just zoom to one of these. Yeah, so these are kind of pictures that you can get of Thurston unit norm balls with this program. So there's of course not just the pictures, but there's a whole data structure there, and you get all sorts of information about the surfaces representing classes, and you can study all of this. So anyway, so maybe this is advertising for Will Worden's program, and you can find all of these things when you just run to his webpage. I shall stop. Okay, thank you.
Thank you, Tillmann. So any questions? I have a couple of questions. So
yeah.
So first one is, do we know what's the dimension of this polyhedron just from the description? So the dimension of the top dimension.
Yeah, the dimension depends just on the rank of the homology group. Yeah.
Oh.
Yeah. So it's in the because it's, am I sharing again? Yeah.
Yeah.
Yeah. As you see here, I mean this is really the dimension here is just determined by the rank of H upper 1 of M with Z2 coefficients. Yeah.
And the second question would be the obvious one about the dual. So do we know what are the extreme points of this polyhedron?
What these kind of extreme points
right.
here are?
Yeah, so they're not the fibered ones, right?
No, so they're not fibered. And yeah, so yeah, I mean this whole study actually. So there's a lot known sort of about the structure of fibered phases. So fibered phases are really well studied. So I could just quickly sort of say, so fibered. So Fried has a way of understanding them using flows on your manifold. So basically associated to each fibered phase, you can actually associate a flow in the manifold, yeah, that kind of characterizes this fibered phase. So even if you change the surface, right, the dynamics of this flow basically stays the same. Then Ertel can sort of understand them using branched surfaces. So he shows that actually for every fibered face, I said here you get sort of infinitely many surfaces, but what Agol tells you is that's actually one branch surface that carries the whole fibered face. Yeah, and here it's known that, I mean, for non-fibered faces, you sometimes one is not enough. Yeah, so there are examples where you actually need more than one branch surface to carry a non-fibered face. And so the question is then, and is there some finer structure in non-fibered faces that one can also understand in other ways? Yeah. Then Ian Agol, and he defines what are called veering triangulations. And he basically shows that, I mean, the veering triangulation you basically build from, I mean, you start with one of these surfaces here, yeah, and then you start sort of building this triangulation. But actually, regardless of where you start in this fibered face, you end up with the same triangulation, yeah? It really just depends on the space. And then also, I mean, there's sort of, I mean, Fried again, I mean, he sort of studies, so in order to think about finer structure, right? I mean, I said the flow is the same, but he has some kind of a normalized dilatation function on this here. Yeah, we talked about the dilatation of these dinosaurs before, right? So you can sort of think about these dilatations, and when you sort of look at this dilatation function, so what he shows is that over the face, it's actually a convex function. So it looks a bit like this here, right? A convex function over this face here. And so it has a minimum, of course, somewhere. And this minimum, you can think of as an invariant of the face. Yeah. And then he also shows that actually in this kind of interval from this minimum to infinity, the image is kind of dense. Yeah. So that's actually also very interesting. Yeah, and again, you could ask, what about the fibered faces? What about the vertices? Yeah, I mean, can you find sort of some better properties there? Mm-hmm.
And slightly different type of questions. So in your paper, you showed that figures that the programming you have written. So what are you using as an input of the information? Are you using the description of H1 of MZ or?
Oh, yeah, so the input for the program is really the manifold.
So fundamental group of manifold.
You could either you can just give it via a triangulation.
Oh.
Of course, there's also a whole census of manifolds. But you could also say input a link diagram. Yeah, so if there's a particular knot or link that you're interested in, you could just draw it. And so this is really using the functionality of, so there's snappy.
Oh.
Yeah, that is basically, that is used there. So yeah, and the program is built on Snappy and on Regina. Yeah, so Regina is a software package by Ben Burton to study normal surfaces. Yeah. Mm-hmm.
Thank you. Yeah, thanks.
Mm-hmm.
Any other questions or comments? Not, just thank Professor Tillmann for wonderful talk. Thank you very much.
Yeah, thank you. Thank you very much for the invitation.
Yeah. Listen, the voice is not audible. You are not audible.
Yeah, so I'm saying that thank you for coming after lots of programs. Time.
Yeah, sorry, Krishnendra, it's very hard to understand you.
I hope it is better now.
Yes.
Oh, wonderful. Yeah, no, it's perfect.
Yeah. So I'm saying thank you very much for coming to this online seminar after lots of postponement of this talk. So we planned it in March first week, and then I got a travel plan, after 2 years. So I thought of making it, and then you have
Mhm.
some job. So finally we have started it. Even
Well,
though
we almost held it on Holy, right?
yeah, absolutely. No, this time Holi was, like normal after a long time. So people
Mhm.
came out and celebrated, which was sort of restricted in the previous 2 years.
Mm,
Yeah,
mm.
so this
Yeah.
time people really enjoyed it.
Yeah.
Yeah.